All right, guys. In this one, we're gonna start with risk, right? And the main question we're gonna ask ourselves is there a way to quantify risk for the patient, and without actually testing them? Okay. So that's the main thing we're gonna focus now. So how do we like classify the risk? In my head, the best way to do it is in terms of disease and treatment. Okay. So when I look at disease, um, I'm gonna have to refer to this section now. Look at the table, okay? So in this table, you're gonna see the disease, like first two columns, right? And then you see the exposure or intervention in these two columns, right? Always remember that disease will, even in the sensitivity table, this will also be at the same horizontal axis, and this will be all the rows will be this thing, okay? Exposure, intervention, or treatment or something, right? So what are we doing is we're first thing we're going to look at is the risk based on event, right? So events rate is something we're measuring when the risk of adverse event in patient group with some factor A. Okay, so there is something we're measuring, like in this scenario will be like factor A, right? And we're dividing it by the total patients in the group with the factor. So I'm measuring the adverse events, right? And it should make sense. Events rate, we're measuring the adverse events, okay? And who are we comparing this to? It's we're comparing this to the controlled events rate, okay? So the controlled events rate is risk of adverse event in placebo group divided by the total number of patients in the placebo group. And these two rates, or basically ratio slash proportions, will help me knowing who is the dominant one, right? Who is getting who is showing me some sort of result, right? So if I compare these two, if first of all, how do I compare these two? I can divide them by themselves, right? So I take EER and divide it by CER, which should make sense because this is control, right? So I want this, I want my like proportion to be compared to like a normal, right? To a control. So now I see, I divide both of them, and I see EER by CER, okay? And that is called the relative risk, right? So I'm comparing the adverse event due to some factor, and then I'm comparing the group with which didn't get anything, right? That is the relative risk. So that was one way of comparison where I get a ratio, a relative ratio between the two, right? Now, if I don't take the ratio and I subtract both of them, that's also giving me some value, right? What is that value telling me? That value is telling me the difference between the exposed and the control. Okay, so the difference between the two groups, right? That's gonna tell me the main factor that I'm looking for. And what are these two things? So even though events rate isn't given in this thing, so what we're looking at relative risk here, and we're looking at attributable risk here, right? So any events rate will be, you know how we see it here, risk of adverse event in patient group A with some factor. So it will be A by A plus B, right? So you see A and A plus B, right? So this will be our adverse effect group. So you have this disease column, and we got the intervention, and then the intervention they got. So the total population in terms of that. So A by A plus B, right? That'll be EER, and control group will be they had the disease but they didn't receive any intervention, or they received a placebo or something like that. That would be C by C plus D, right? So I got the ratio. So now my EER and CER is solved for. Okay. So remember that first of all. Now, what is relative risk? I'm dividing the two. So I'm dividing the ones who actually have something by divided who actually got some treatment or something, divided by the ones who are in the control, right? So that I get the ratio of that. Okay, and it should make sense to you. Otherwise, remembering the formula becomes difficult, right? So you take this table and you take the first row, first column divided by the first row. Okay, got the numerator. Take the second row and divide it by the like the rest of the row, the columns. So a by A plus B divided by C by. If there is association present, the relative risk will sniff it out. Okay. So if the, and this should make sense, if the numerator is greater than the denominator, it's always going to be greater than 1, right? And if the denominator is greater than the numerator, you're going to have less than 1. So what does that indicate? You use this example to help you understand it, right? So if I have radiation poisoning or something, I am 5 times at a greater risk of developing some sort of cancer. Or let's say a person smokes and they're 10 times more prone to getting some lung disease or something, right? So that tells me the association between the two variables. Okay. So this should make sense. And always, if it's equal to 1, that means the numerator is equal to the denominator. That means there's no association between exposure and the disease. Okay, and we haven't gotten any result out of it, right? Now, well, this was the first way. So we divided the EER and the CER. This should make sense now. Now, what was the second way? We're gonna subtract them. And what are we looking for? We're looking for the difference in risk. Okay. So how does the exposed group compare to the unexposed group, and what is the magnitude between the two? Okay. So we're taking the A by A plus B minus the C by C plus D. Okay. So this should be attributable risk. How much can I attribute it to the exposure? That's the question they're trying to answer for us. All right. And if you want the percentage, all you have to do is take the relative risk. So if you just take this RR and put it into this equation, you're gonna get AR percentage. So that helps me remember this thing. I usually forget like what comes first, what comes last. If you find a better way, you can. I just use maths. I just divide each of the terms by RR, and that helps me understand. Okay, so I'm taking the whole, which is 1, so the 100% minus dividing the exact ratio of relative risk. Okay, so this formula is also should be easier to understand now. Right, so we did these two things. Now the next thing was odds ratio. Okay, the odds ratio, the best way to understand is that something happened or didn't. So something happened or didn't happen in the exposed group divided by something happened or didn't happen in the unexposed group. Okay, now you come back here. So in this case, we're not just measuring like the disease and intervention and stuff. We're also measuring. I mean, we can measure anything, but we're comparing the two. So, and we're trying to get the like the proportion between exposed and unexposed. Here we were just looking at adverse events, right? But here we're using it for exposed and unexposed. And what is the best way to get exposed and unexposed is using the case control studies. So cases are the ones that we are basically categorizing as exposed, right? And controls are the unexposed. Okay, and it's also like retrospective and stuff. So we use odds ratio to basically tell ourselves, you know what, these are the odds of this person compared to a normal person. Okay, so that's the question we're answering to odds ratio. And similarly, if the numerator is greater, that means the exposure are odds of exposure are greater in cases. Okay, and if it's less than 1, that means the denominator is greater. That means odds of exposure are greater in controls. Okay, and what are we doing? So we're taking the disease group, right, and we're comparing the exposure levels in that group first. So all my cases are here first, right? So that's the numerator. Okay, and then I'm dividing it by the controls, right? So that's and I'm comparing the exposure levels in those things, right? So I'm dividing the B by D. So you see how exposure is B now, unexposed is D. So that's just the ratio now, right? And then when you simplify, you get AD by BC. So you just do cross multiplication, right? A into D, B into C, and you get your odds ratio. All right. So now moving further, we have something we use with treatment. Okay. So far we were giving attributable risk, relative risk, and stuff like that. So these are more suited to like a disease and how prone to you are to getting the disease and stuff. But now we're looking at risk reduction. Okay, so we're usually looking at the same formulas, but in terms of like the treatment stuff. Okay, so we were doing EER minus. I think so we were doing control minus the EER here. Now in this one we're gonna do the opposite. Okay, so you come back here. So the absolute risk, right? Absolute risk reduction. Yeah. So if they ask you to calculate just the absolute risk, it'll be these two things, right? So absolute risk reduction is the difference in risk, not the proportion attributable to the intervention as compared to the control, right? So you gave something and now you're measuring the difference between the two, right? So you see how the opposite of attributable risk is this thing now, all right? So come back here to the table, and this will help you understand more. So we're taking the row which has no intervention, right? C by C plus D, and we're subtracting the group which has intervention, and we're seeing how much we have reduced the risk of this person, right? So absolute risk reduction, right? And if I take, so and the next thing that we're going to look at is this number needed to treat. Best way to understand this is through these statements. Okay, how many do I need to treat to get one patient cured? Okay, so if I'm trying to answer this question, what I do is I take my absolute risk reduction, and when I do like 1 divided by ARR, I get my number needed to treat. Okay, so what is this signifying? Is it's just signifying that if this was like, you see the numerator is 1, why is it 1? It's saying that if I need just one patient to treat, like to be cured properly, how much of this like apps this treatment is helping me to do so, right? So how many patients do I actually need to treat using this drug to get one actual patient cured? Okay, so NNT is equal to 1 by absolute risk reduction. Okay, so this was about treatment, and we looked above was about diseases, right? So number needed to harm, that we can use the same maths to come up with this. Now what is this? 1 by absolute risk. Okay, how many need to be exposed for one patient to be harmed? And both of these are important questions to answer, right? So if I come up with a basic ratio, like a standardized way of saying that, you know what, the NNH of this let's say virus or something is 5, like I need 5 people to be exposed so that one person is actually harmed. Okay, that's something. But what if it's 200? What if it's 500? That's better actually. If I expose 200 people and only one gets harmed, that's actually better. But if it's like one person in every 5, then that's a problem. Okay, and similar to this one. So NNT, what is good? If I'm treating 5 patients and one patient is cured, that's pretty good. But if I'm treating 200 patients and I'm getting just one patient who's cured, that's a problem. The treatment is not as effective as it should be. It needs to be changed. Something needs to change. Okay, so both of these ratios help us in answering that question. Now, next thing, and we discussed most of these. Now, these fall into a different category of like population and population maintenance and stuff. Okay, what is case fatality rate? As it says, fatality, mortality, more or less the same thing. Okay, percentage of deaths occurring among those with the disease. So deaths divided by cases. It should make sense. Okay, so if 4 patients died in 10 cases, you have this. What is mortality rate? Mortality is again, it's related to the number of deaths, but we have standardized this rate. Okay, what do we do to standardize it? We take the total number of deaths, but we define it in 1,000, like specified number. So in this one, we take, first of all, the specified number is 1,000, and we also specify the time period. So it's always going to be year. Okay, so take a look at in this example. If 80 people were in a town of 10,000, like die, 80 people in a town of 10,000 die. So 80 people died in over 2 years. So understand or rephrase the problem again, right? So 10,000 people died, and no, sorry, 10,000 people are there in a town, right? 80 people died, and this is taking place in a span of 2 years. Okay, that's the question they're asking. Okay, what is the mortality rate? So mortality rate will be, you take the total number of deaths. So this will be 80, right? Now divide this by divide these two numbers. Okay, so you take 10,000 divided by 2, you get 5,000. Okay, now what do you get? So 80 divided by 5,000, and then you simplify it, so you have 1,000 in your denominator, because that's the standardized way, and that's how I actually do it, right? I think I've mentioned it here as well. Yeah, you see. So you take the mortality rate, and that's in one population divided by 1,000 people per year, right? So total population So what is this 1,000 people per year? It's total population divided by total number of years, right? For example, if the total population is 2,000, right? Sorry, 20,000, and the span of years that I'm measuring this population in is about 4. So in 4 years, I'm measuring about 20,000 people. Okay, so this simplifies to 5,000. Okay, and in my example, I'm taking 50 deaths in that 20 in those 20,000 people, which is like quite low, but still. So what am I doing? I'm taking the 5,000 in the denominator and I'm taking the number of deaths in the numerator, dividing the two. And now what do I get? 10 in 1,000 deaths per year. So the mortality rate is of 10. Okay. So I always divide. So this helps me because it was harder for me to understand what like population per year and how to standardize it initially. But all I do is divide the number of the total people they're given me divided by the number of years and try to divide it in such a way that I end up with 1,000 in the end. Okay, so in this case, it was I made the operation simple. I just used 50, and this was 5,000, so I just divided it, and then you get 1,000 deaths per year. So the mortality rate is 10. Okay, so that's the mortality rate. What is attack rate? Attack rate is proportion of exposed people who become ill. So people who become ill by total people who are exposed. Okay, so attack rate is similar to incidence, right? But attack rate is basically in terms of like a contagious disease or something. Okay, but incidence can be for any sort of disease. All right. So this was risk and stuff, and I'll come back to Kaplan-Meier curve. We've done most of this. Okay. So let me go into stats now. All right, I've tried to simplify stats as easy as possible, and I'm mostly following, like, I'm not going deep into statistics and stuff. If you want to watch some other playlist with more technical details, I'm just focusing on what we need to know in order for USMLE Step 1. Okay, so first things first, you're always going to see the normal shaped bell curve. Okay, and this term of central tendency is always going to come. The best example for this is like, let's say you have like a jar full of like sugar or salt or something, right? And you pour it out on the table and it forms like a heap, right? So if you pour it directly from the top and it creates this heap, that's the heap we're trying to visualize here. Okay, that is the central tendency. Okay, and it's seen that most of our data, like most of our data falls is always normalized in some way. It's normalized, and normalization means this central tendency. Okay, how do we measure that central tendency? Is by the 3 M's. Okay, mean, median, mode. All right, mean, I'll come to mean in a sec. Median is always in the middle. All right, median is the number that falls in between the entire set. Okay, and mode is the number that is repeated. We all know this. Okay, and mean is the average basically. Okay, what we need to understand, and the questions will always try to trick us with, is the outliers effect. Okay, so if there are outliers in any data, that means they don't coincide with any of the spread, any of the normal spread. They're somewhere here or somewhere at the extremes. Okay, those are outliers. They might give you box plots to look at the outliers. How does a box plot? So even if they give you this thing, please make sure you know it. All right, so you know this. Okay, so this is also a measure of central tendency of the data. But what I want you to look at is these points, right? So these are the outliers, right? Even though you might not see it in all of the stats examples, they might try to switch it up and give it in as like an experimental question or something like that. Okay, so this, try to remember what all of this means. Okay, all right. So if there are outliers, most affected central tendency marker is the mean. Okay, remember that. And the outliers effect if it's greater than the overall mean value. Okay, if the outlier is greater than the overall mean value, what do you get? You get right skew. Okay, or what else do they call it? A positive skew. Okay, what does that mean? The tail is to the right. So skew we're looking at is the tail. Okay, the tail end of the graph, and I'll show you this into a second. Meaning the mean is always to the right. Okay, so you come down here and we start to look at the skewed graphs. Okay, this thing. So positive skew, you see the mean is towards the tail. Okay, remember this. Mean is the most affected by the outliers, and it goes in the direction of the outlier. In this case, we have large number of like outliers which are like large in number compared to the mean. Okay, so the mean will follow that trajectory, that direction. Okay, what happens in negative skew? The mean follows the lower values, because you can understand the average will tend to go in the direction of where the most extreme values are, right? So this is negative skew. So we have two types of skew. You have left, so the tail is to the left, meaning the mean is to the left. Okay, right skew, you have the tail is to the right, meaning the mean is to the right. Okay, mean is most affected by this. Median is not really affected, it's always going to stay in the middle. And what happens to the mode? There's no outlier effect. So if ever they try to confuse you with what's changing, what's not, which direction is this, what direction is that, always try to remember mean follows the tail, and mode is always the one that's away from the skew. Okay, right, so that was the initial introduction. Now, because now this concept of standard deviation and variance, try to understand in this way. So you see the purple graph, right, and you see the blue graph. The difference between the two is how further apart the graphs are, right? So you see the height difference. So if the blue was closer to the purple shape, you would see that the variance is decreasing. Okay, so the variance is basically the degree of furtherness, or the degree of variable data. Okay, so if what's good for us is to have like a well shaped data, like good nice distribution of data is having low variance, because variance means that the data is far spread apart, and it's not actually indicating anything, it's just not following the normal distribution. Okay, so this is variance, right? What is standard deviation? So you see how variance is just like a measure of for degree of furtherness. Standard deviation is like a stepwise demarcation. Okay, so what is this stepwise demarcation? um, so stepwise demarcation of distribution, what do you have? You usually follow the normal distribution. Now this normal distribution is also called the like two tail distribution, because you see it has one tail on the right, and it has one tail on the left. Okay, and down the middle you have positive values to the right and negative values to the left. Or if it's like, if the mean is not zero or something, you can have like greater values on the right and lesser values on the left. Okay, that is what this means. So wherever you see standard deviation, there is this phenomena that occurs, right? You see this thing, right? So you have positive standard deviation, that means stepwise demarcation of the values. Okay, the total number of values. And every stepwise demarcation, it helps you to gauge what the actual number of like the actual data is. Okay, so Gaussian also bell shape, mean median mode. For normal distribution, mean is the best, and for skewed data, median is better. Okay, so they can and they have asked questions on this, where you take 68% divided by 2 to just get this half, or if you want this half, you have to like subtract all of this and you get 99% of this. You know, they've asked you a lot of questions in that sense. I'm not going through questions in this video, but what I do suggest is going to Google Gemini or Chat GPT and just asking it to form some like statistical questions for USMLE. Okay, and see what you get out of it. If you can basically identify the standard deviations and how to subtract to get those standard deviations, it'll help you a lot. Okay, so always remember, one standard deviation, you have to specify in which direction. Okay, if it's one standard deviation, that means it encompasses both the positive standard deviation and the negative standard deviation, and both of them equal 68%. And if you take two, you have two positive standard deviations and two negative standard deviation, that will equal to 95. Three standard deviation, it means positive, three positive standard deviation, three negative standard deviation, that will equal to 99.7. All right, so you have to specify which direction the standard deviation is actually in. Okay, since standard deviation can be positive or negative, and it does not capture the spread of the data, we came up with squaring the thing. So if I square a negative value, it turns into a positive value, right? So if I square the SD values, all the values will be positive now, and that's what the variance is. Okay, so you don't have to remember this formula anymore. You just have to make sense of it. This thing, right? Variance is equal to standard deviation squared, right? Why did we square it again? First of all, I don't want negative values in my data. Okay, I want only positive values for better understanding and visualization. First of all, and standard deviation itself, it does not capture the exact variance. Okay, imagine this, if this was an animation, imagine this contracting and spreading apart, right? If I want to actually define it in terms of an actual like value, variance is more suitable in terms of greater than like standard deviation and stuff. Okay, so once we have variance, right? So variance, if variance increases, you have greater spread. Okay, you see this, and if you have low variance, you have low spread, right? You see this, and we try to minimize variance in terms of like the robustness of the data or what the clinical significance of the data actually is. Okay, but you see how now if I increase standard deviation by just like 1 unit or 2 units, the variation will increase by squared of that. Okay, so this is like they are like proportional, but there's like exponentially proportional, right? So there will be squared. Okay, there's just a observation I need you to keep in mind. Now we understood what standard deviation is. Now there's something called the standard error. Okay, what does the standard error do? It compares the same thing to it compares something to some standard slash generalizable thing. Okay, because what I'm trying to do with standard error is I'm trying to figure out what we actually do is like we conduct experiments in the lab and stuff, right? And what we're trying to do is trying to extrapolate that data in terms of the population, right? So if I conduct a study based on just 100 participants or 1000 participants, how does this data compare to the overall populational data? Okay, this is what standard error tells us, right? And why is it error? Okay, why is it called error? Because we are comparing our lab grown data, our lab found data, and comparing to the standardized slash populational slash generalizable data. Okay, so wherever you see this error thing, we're trying to take something and compare it to a like a standardized value. Okay, and what are we doing in this case, right? So you take the standard error, okay, sorry, you take the standard deviation, right, and you divide it by the square root of the population, the total sample size you have. Okay, what this does, it orients the standard deviation in such a way that now you know what the populational effect is, the whole sample size brings. Okay, now if I square these two sides, okay, if I just square these two sides, I get standard error squared and I get standard deviation squared, and I remove the square root here. That's the only reason I did it. Okay, so what did I write here? Now I know the difference of variability between my testing population and my total population. Okay, so that was the thing that we're trying to find out here. So now we squared it, and now you see what happens. This standard deviation squared turns into variance, right? And if I take variance and I divide it by the total population, it will give me the standard error squared. This is only to help you understand. This will not actually be like a problem or something like that, but they might give you variance and you might have to like square root it and get your standard deviation to get the standard error. That could be a problem, but this whole exercise is basically to help you understand. So now visualize this. Variance is the spread of the data in the sample, okay, and n is the total population or your sample size. Okay, the ratio of the two, okay, the division of the two helps you get the square of this standard error. Okay, and what does that actually signify? If I increase n, right, it was tougher to visualize the like increasing n and what actually happens to standard error and stuff. All right, this is the only roundabout way I came up with to help you understand that. Now if I increase the n, that means I'm increasing the denominator. Okay, what am I doing? here, right here, if I'm increasing n, okay, I'm increasing the denominator, the overall value will decrease, right? So standard error will turn into this small square right here, okay. But if I decrease n, if I decrease the sample size, what happens? The overall denominator decreases and the overall variance and stuff will, like, the overall value will increase, right? So standard error will be large. Okay, this is to help you understand all of these things. Now you see how standard error is just given as this and you standard error as n is equal to this. It makes sense even more now that we've gone through all the intermediate steps. Okay, so you see that the stuff here, standard deviation, how much variability exists in the data around the mean of these values. And what did I say? It's like demarcation, like stepwise demarcation of the data, okay, around the mean. What is standard error? An estimate of how much variability exists in a theoretical set of sample means around the true population mean. Okay, so we took a sample theoretical set and how much variability exists compared to the true populational mean. Okay, now so we understood all of these things. Great. Moving forward. All right. So what is this bimodal distribution? I suggest we type in. Let me just check bimodal, because this bimodal distribution comes up in a lot of diseases, and I'll tell you what this is. Okay. So one is this Hodgkin's lymphoma thing. What is bimodal distribution? Is basically it has two peaks. Okay, bimodal mode. Okay, so it occurs in two instances, right? So you see, in terms of like our whole diseases and stuff like that, you can have a disease in the young and you can have disease in the old. So whenever you see this bimodal distribution, you have disease in the young and you have disease in the old, and that's why we'll look through other stuff as well. So you have Hodgkin lymphoma in the young adults and you have Hodgkin lymphoma in the older people. Let's see where else do we see bimodal stuff. I think that's it. Yeah, I think that's it. Okay. So, and this is the only example they've given us. Suggest two different population. Example, metabolic polymorphism such as fast versus slow acetylation. So, wherever this bimodal distribution in terms of diseases is just by like the age of onset. But if you have any allelic distribution, which one common, there is two common alleles that are present, we can also trace a graph based on that frequency and stuff, right? So that also matters. Suicide rate by age, it could be that young adults have more are more prone to suicide, and like older adults might also be. So it has some like different peaks. Okay. Now, most of us get confused with this thing, right? And I've tried to break this down as easily as I can. Okay, this statistical hypothesis testing. So, how do we actually compare? Now, ever since this video has started, what I've always reiterated is that we take a normal, a base or a standardized value, and we compare it to something, an alternate, or some like exposure, or some treatment or some disease, some aberrant value, right? So statistics or basically hypothesis testing is the same thing, right? We're trying to compare a standard value to some alternative. Okay. Now, what is this hypothesis and what is this null hypothesis? What I suggest is, try after you're done here, try to look for examples through these Gemini and stuff to about null hypothesis, and I do have some examples, I think. So I'll show you what like some null hypotheses actually are. Okay, so null hypothesis is basically called the skeptic's position. Okay, so the skeptic will say, oh, there's no connection, there's no association, there's no problem, nothing is gonna change, nothing's gonna happen. That's the null hypothesis. Characterize it. Okay. And the alternate hypothesis is the challenger's position. The challenger is saying, you know what, there is a problem, there is a association, there is something, right? That is the alternate hypothesis. So wherever you see that, let's say in a study sample, you're trying to see if there is a link between like eating junk food and high cholesterol or like atherosclerosis or something, right? So the skeptic will say, no, there's no association. Okay, it's simple. There is simply no association, and then you have to disprove that. And who is the challenger in this case will be, yes, I there is an association, and then we have to prove that. Okay, so it's all about proving and disproving these two characters. All right. So come back to the definition now. Null hypothesis, also called H naught hypothesis, is no difference or relationship. There is no association or risk factor and stuff. Okay. Alternative, there is some difference or relationship. Easy. All right. We need this, and now we can move forward. All right. So we understand what the null and the alternative hypothesis is. Okay. Now what we have to remember is to to actually approve something. Okay. To accept something, either we prove that this is right, either we prove alternative hypothesis is right, or we disprove the null hypothesis. These are the only two ways that this can occur. Okay, and you have to remember that fact in mind, that it's easier to reject something than to actually prove something into being. Okay, and this fact is also laid out in first aid as well. All right, so how do we first know how valid something is? Because I'm conducting a test, okay? I'm conducting this test and I'm looking for like actual difference between the alternate and null. But how do I know I'm actually conducting it properly, or how valid this whole thing is? Okay, that value, that trueness is brought to by us by p-value. Okay, and what is p-value is the probability of obtaining extreme results. Okay, so if p-value increases a lot, that means I'm getting a lot of extreme results. Okay, and that means maybe the whole study is not actually valid. Okay, that's what p-value indicates. But if p-value is lower, that means it's a solid test, and everything is valid and everything is going according to plan. All right, so how do I treat the null and the alternate hypothesis in terms of p-value? All right, if p-value increases, that means it's greater than 0.05. That means if I convert this into percentage, that means more than 5% of my data is showing a lot of extreme values. Okay, what does that mean in terms of my validity? Observed data has shown that there is not enough proof to reject H naught. You don't have enough credible proof. You don't have enough valid proof. Why? Because like over 5% of your data is muddled, right? It's not effective anymore. So that is the principle of high p-value. But if I conduct a study which I find the p-value to be less than 0.5 or equal to 0.05, right? That means that I have enough data that has shown that credible data that has shown that alternate hypothesis can be true. So what did I do here? I'm trying to prove alternative hypothesis with good solid data. But in this case, because I don't have enough solid data, I cannot even reject the H naught, let alone prove HA. Let that be, because both of them are trying to achieve the same thing, right? Prove like HA is actually the main thing, but I don't have enough evidence in this thing. So now you understand what the p-value is. Okay, so give it a characteristic. Okay, so it's moderating these two. It's basically like serving as like a security guard, like making sure that everything is working properly. Okay, probability of obtaining test results as results at least as extreme as those observed during the test, assuming that H naught is correct. You have to assume H naught and then see how the validity of the data changes. Okay, so that was one way of knowing who is actually true. First, we build like a validity area around it. Now, the next thing is, how error prone are you? Okay, so we asked the question, how valid are you? Now we ask the question, how error prone are you? Because these are two different things. And if I start seeing who actually contains the error, it will tell me which one is actually true, right? And which one like I should accept. Okay, so how do we actually demarcate this? Okay, what I've done here is I've taken the testing errors, right? And I'm a third person looking into the study. Okay, that's my perspective right now. So I assume the true reality. If the true reality is that the alternative hypothesis is true, This is like completely true. This is what actually happens. Okay, the HA is true. Or if in a different reality, H naught is actually true. Okay, first get that into your mind. Okay, so my true reality is actual HA is true, and my true reality can be my actual H naught is true. All right. What's the next step? I take that. All right. My true reality is HA being true, and what now my study is basically trying to prove if I'm right or not. Okay. So I assumed my true reality, or I give my true reality, and I'm seeing if my HA or my study is actually finding that out or not. Okay. So what did I do? I have a study which accepts HA, or a study that rejects H naught. That means I have basically confirmed like what I was given. Okay. So read that again. Study accepts alternate hypothesis. Good. That's good because our reality is HA. That's good. Study rejects H naught. That is also good. Good job. Because you have rejected H naught, that means automatically you have proved that HA exists, right? So this is a good job. Good job. This we need this, right? What's the other hand? Study does not accept HA. So you made a study in which the reality was HA to be true, but your study does not accept HA. What's the problem? What did you do? Something happened. Something was wrong, right? Or you have a study which does not reject H naught. You see the comparison between these two, and this was the reason I made it this way. I could have given you the table as well, try to explain it through there. But you see the comparison between these two, right? Study does not accept HA. It's not accepting your study that you've built is not accepting the reality. Or you have study that does not reject H naught. If I don't reject H naught, that means H naught can be true. That means I haven't done my job. Okay, that is another scenario. We understand that so far. Okay. Now we look at H naught. In this reality, null hypothesis is true. Right? In this reality, null hypothesis is true. And what are we looking at? We made a study which accepts H naught. Good job. Reality was true, and I made a study that accepts H naught. Good job. Or study that rejects HA. That also makes sense. I rejected the alternative. You have study that rejects H naught, right? Or a study that does not reject HA. This should be reject. This shouldn't be accept. Okay, that does not reject HA. Okay, so I've not been able to reject my HA, and that means H naught is not true. Okay, but in reality H naught is true. Anyways, so what does this all mean? So you come back to this table again. So I have my reality HA, okay, and my study accepts HA. This is good. And what do we call this? We call this the power of the study. Okay, power of the study. How do we get the power of the study? What we do is we go through this exercise. Is that HA is true? Okay, reality is HA, but study does not accept HA, or study does not reject H naught. That is my error. Okay, this is the beta error. Okay, so my reality was HA, like alternative hypothesis, but I've not proven it, or I've not declared it. Okay, and what does this actually mean? It says, well, your study showed something significant happened, but you are saying it didn't. So that's what the beta error is actually saying, or the type 2 error is actually indicating, is that either something significant was there and you don't know about it, or you didn't show it, okay, and you're reporting it as if nothing happened, okay, and you see something must have happened, but you are saying it didn't, right? That is the false negative error. So type 2 errors are false negative errors, right? So I'm saying something else compared to what actually happened, okay? And these are the two principles of alpha and beta errors. In beta error is a false negative error. Something must have happened, okay? Something must have happened, but you are saying it didn't. What is that something? Something is HA. HA in reality should have happened, but you're saying it's not. What's the discrepancy? What's the issue, right? That is the beta. And if I just compare power, how do I get power? Is I take the 1 minus beta. So I take the error probability and subtract it, and I get the power, entire power of the study. And this is good, because if I have a study which accepts HA and rejects H naught, I did my job. I came up with something credible, and it's statistically significant. Okay. So power is basically how good are we at finding different solution methods and answers. Higher the power, greater the study. Okay. And beta always trumps alpha in terms of value, because I want to be able to get some credible result. Okay. And that's why I have to minimize beta, and we'll talk about that a little bit more. Okay. So now we understood beta and 1 minus beta. So if H naught is true, okay, if null hypothesis is true, and I've just accepted that, you imagine, like, I came up with a study that says like there is an association between high cholesterol and atherosclerosis. Okay, that's my study, but very simple. And my null hypothesis is that there is no association. Okay, and after my study, I found there is no association. Okay, what have I done? I've done nothing. I've just proven myself that nothing happens. So we did nothing basically. Okay. um, that is this column, and now you have H naught, and study rejects your H naught. Okay, so it's leaning towards your HA, right? So what are we making is that we have we in reality H naught, matlab, like null hypothesis must be true, but what do? We're saying the alternative is true, right? So we're saying, what are we saying? Well, your studies show nothing happened, but you're saying it did, right? Nothing. You're not supposed to do anything, but you're saying something happened. You're falsifying your results, right? Or other way of saying it is, nothing must have happened, but you're saying it did happen. Why did it happen? Right? This is a false positive error. And a lot of people try to make these things up, like, to get like a good credible results and good statistical results, right? So they try to commit alpha errors in order to get a positive result, right? So this is basically a false positive. I'm declaring something happened, but nothing actually happened. In this one, I'm saying I'm hiding the results. I'm saying, you know what? There is no result. There is no correlation. And sometimes people actually do that. I think there was like a Alzheimer's study, which like didn't actually make some sense. I think there was a lot of errors in there. All right. Anyways, so now you understand the intuitive sense behind alpha and beta, and then you come back to this thing. Okay. See this. Now this should all make sense now, right? I divided this table up into this chart. Okay. And try to remember this chart as best as you can. It'll help you visualize this whole thing. All right. Take a look at this, and this should all make sense to you now, right? Type 1 error. Just let's just read through it. Stating there is an effect or difference when none exists. Makes sense. Alpha is the probability of making a type 1 error. Okay, usually is less than 0.05. Makes sense. If P, the probability is less than alpha, okay, if the probability of error is less than alpha, then assuming H naught is true, the probability of obtaining the results would be less than the probability of making type 1 error. Okay, what is this whole complicated thing telling you? Only thing it's saying is, if I set a probability value, okay, and for my study, and if it's less than alpha, so basically what I'm saying is I don't want to make the errors, the alpha errors. That's it. Okay. And H naught is therefore rejected as false. It's good, because if I start to say that, you see here, right? If I start to say this, like nothing happened, right? Even though something must have happened, then I'm no. If I declare something happened when something actually didn't happen, then I'm falsifying my entire study, right? So this whole sentence right here is basically just saying that thing. Okay. And this statistical significance and clinical significance, and this they've mentioned here as well. Statistical significance is defined by the likelihood of study result being due to chance. Okay, if there is a high statistical significance, then there is a low probability that results are due to chance. Okay, so if I, for example, if I just conduct a study and I throw some random data in it, it will still give me some positive values, some negative values, and that is just by chance. Some things just happen naturally, and naturally you get good results, you get bad results. Okay, but if I improve my statistical significance. That means I'm reducing the chance values. I'm not leaving it up to God or nature or environment in terms of my results, right? I'm controlling these variables properly, so I gain statistical significance in that. But getting statistical significance doesn't actually mean you're getting biological or clinical significance. Okay, what is this? Is the measure of effect on treatment outcomes. Like, this is proven stuff. Like, I actually see it with my own two eyes. Physical changes are occurring. The patient is getting actually better. They're receiving this thing, or something like that. This is clinical significance. An intervention with high clinical significance is likely to have a large impact on patient outcomes and measures. Right? It's physical. Like, it's actually, I can see it. Right? And this is more like a theoretical significance. Okay, so, and I've said this before as well, you can never prove the alternate. Okay, but you can reject the H naught as being very unlikely, right? It's easier to reject than to accept. Okay, and what are we rejecting? We're rejecting the H naught, and if I do that, I'm getting, like, I'm doing my job well, right? This is the alpha error, right? What is the beta error now? We've seen this. The HA is true. Okay, the true reality is that alternate is true. But what you're saying is, you know what? There's no change. Nothing happened. Okay. And stating there is not an effect or difference when one exists, and H naught is not rejected when it is in fact false. Beta is there for the probability of making type 2 error, and statistical power is 1 minus beta. Generally, when type 1 increases, error increases, type 2 error decreases. And it makes intuitive sense, right? If I'm saying that, if I'm saying that something is occurring when it shouldn't, right? If something is occurring when it shouldn't, I'm automatically also saying that I'm decreasing this value, right? I'm not saying this thing anymore, right? So intuitively, I try to make sense between these two in that sense. But usually, what we're trying to achieve is reduce the beta error far more compared to the alpha error, and I'll tell you why. Okay. So now we've understood through the diagram I made. So let's just quickly go over the testing errors in this. All right. So type 1 errors, basically false positive errors, right? H naught is actually true in reality, but you see, H naught is true in reality, but we have a study that rejects that. Okay. So if I have that, and now we see alpha is the probability of making type 1 error. If P, capital P, is less than alpha, then assuming H naught is true, then the probability of obtaining the test results would be less than the probability of making type 1 error. So what is it saying? Is saying that if the P, the capital P, the probability I decide of the study I'm conducting, okay, if I decide that to be less than alpha value, right, I'm basically preventing myself from making type 1 errors. All right. But there is a trade-off, that if I basically restrict myself from making alpha 1 errors, kind of decreasing the power of my study as well. And I'll talk about that trade-off and balance more, okay, as we go forward. And something called statistical significance and clinical significance. Okay, what does this mean? Statistical significance is basically like theoretical significance. Okay, and we're basically limiting our chance, right? We're limiting our environmental variables, our patient variables, all of that. We're trying to limit that and trying to gain significance based on just theory. Okay, and clinical significance is the actual practical significance. Okay, measure of effect on treatment outcomes, right? An intervention with high clinical significance is likely to have large impact on patient outcomes and measures. So this is like a physical, I can actually see this change, right? Statistical is more of like a theoretical and study likelihood type of thing. Okay, and obviously the these statistical and clinical significance don't usually translate to each other. Okay, especially if you're making a type 1 error. If I'm saying something is positive, okay, even though it isn't, I'm not going to have any clinical significance in that, even though it might show some sort of like statistical significance or something, or vice versa. Okay, so we know this now. Type 2 errors, also called beta, right? Beta is the probability of making type 2 error. Statistical power is 1 minus beta. And how do we increase power and decrease beta? Okay, this is the main thing that we have to focus on, is how do we detect HA when it's true. Okay, first and foremost, you increase the sample size. Easy. Okay, if you increase the sample size, you increase the validity of the data. Okay, increase the expected effect size. This basically is saying that the number of people in the study is similar to the sample size. The number of people in the study who are actually seeing an effect, I increase their population as well. All right. So you know how you have attrition and stuff and people drop out. If I conduct a larger study, or if I conduct a mass study with like less attrition, I have greater effect size. Okay. Next, you have precision of measurement. Easy, because if I make mistakes in putting my data in, okay, I make mistakes not conducting the proper protocol or proper methodologies, okay, I'm going to have differential results. I'm not going to have the same results, okay. Now, this is where the thing is important, okay, the trade-off, what I was talking about, increasing the alpha level, okay. Increasing the alpha level, how does it increase the power? And that's the question, okay. I want you to look at I have the explanation here, but I want you to look at the plot for type 1 errors. All right, similar to what the thing was in sensitivity and specificity stuff, right? Okay, please open. So these two peaks, even though they're not as visible, yeah. So these two peaks are basically the the two hypotheses, okay, and the data that supports those two hypotheses, okay. So null hypothesis, this is the graph. You have alternate hypothesis, this is the graph. And similar to what the mistakes we were making in that table, you see, the type 1 errors are the false positive errors, okay, and the type 2 errors are the false negative errors, okay. And if I decide a p-value, all right, if I decide a p-value compared to like what is less than alpha and stuff, so I have to mitigate a trade-off between the two, right? Similar to what we were doing in when we were finding the cutoff value for a diagnostic test, right? Same similar thing we are trying to do with this analysis as well. We have to find uh, a value, a p value for the test, not small p, a large p value for this test where I have decreased where I have maximum power of the test. Okay, how do I do that? First of all, alpha levels do not matter as much as beta levels. Okay, that's the main thing, because if I decrease the beta levels entirely, my overall power will increase. Okay, and what are we trying to do? We're trying to shift this towards the left. Okay, we're trying to do this. All right, you see, if I put the marker right here, this line right here, I'm taking in more of the alternative hypothesis in, right? So now you visualize this, right? And if I take the more of the marker in, what am I doing to the type 1 error? I'm automatically increasing it, right? And how does that make sense? I have to increase alpha level to increase my power. How does that make sense, right? So you have to intuitively think about it, is that there is a balance, okay? And what is this balance? It says that imagine alpha is like a net, okay? It's a large net, okay? If I increase the alpha value, I increase the area of the net, okay? If I increase the area of the net, what am I actually capturing? What is alpha value actually telling me? It's telling me, you know what, these are supposed to be h naught values, right? I'm supposed to be h naught in reality, but you're saying that I'm something else. But in doing so, all of these data points also bring about the proof for alternative hypothesis as well. Okay, so if I increase the alpha value, I'm increasing the overall net size. Okay, and I'm increasing the overall power. Why? Because the data that I'm getting because of increasing this alpha size is also helping me prove my alternative hypothesis. Okay, even though I may have some like cutoff where after which all of the errors are occurring and all of the problems are occurring. We don't want that. Just before we reach that, we're gonna set the alpha value such that I create this optimal net, which I get all the data points in, which supports my alternative and not push me towards grievous errors. Okay. So, what is high alpha value? It's good for us. It increases the power. What is a low alpha value? It's a stricter test. It's strict. It's a smaller net, and it makes no mistakes. Okay, and you would think that this is a good thing, right? We don't want to make any mistakes, and that is obviously that's a good thing. But there has to be a leeway to allow data to actually reflect on the alternative hypothesis as well. I don't want to constrict the data by limiting its alpha value. Okay, but I don't want to make the grievous errors, and that's the trade-off. Okay, first of all, that's just with alpha, right? Now, what is beta? High beta is always bad for us. That's simple. High beta is always bad for us. Okay, and low beta is the main thing that we're trying to focus on. Okay, increase the ability to detect the effect. As beta decreases, I'm trying to detect the effect. Okay, low chances of missing the true difference when it comes to beta. Okay, as beta decreases, the chance of missing the difference decreases. So as I said, low beta is more important than low alpha. Okay, 1 minus beta, that means power is ability to detect the change. Researchers decrease beta and keep alpha at a reasonable level, because if I don't keep alpha at a reasonable level, either I am only focusing on the data that actually just supports uh, like that either does nothing. Okay, it neither supports my null hypothesis properly nor supports my alternative properly, right? And what are the other parameters? As I said, you have measurement error, decrease that, sample size, increase that, choose correct statistical tests and stuff. And there's something called stratification and blocking. In this, what you do is divide, in stratification, you divide the study samples into subgroups and analyze them separately. Basically, like a methodology that they follow. And blocking is basically during the sampling, you randomize the thing, okay, the samples, okay, and ensure groups have similar distribution, right? So this was alpha and beta, all right? And you come back here. This should make sense to you now. Why am I increasing alpha level? Because I am trying to increase the statistical significance level, okay? If I increase that, I push the graph, okay? I push the graph right here. Even though I'm increasing type 1 error, I'm trying to prove alternative hypothesis more. That's what I mean, okay? This is what I mean, right? And is there any other graph that is better? Yeah, you see this, right? You see this, right? Alternative hypothesis 1 minus beta. This is the beta. Trying to decrease beta to a really low level. And in doing so, what I will eventually and inevitably do is I will increase the alpha level. And that's fine, because this alpha level is allowing more data to support my alternative hypothesis. And that is fine. We need that. That's good. Okay. But it's held at a reasonable level. So I'm not crying wolf, right? And that's the analogy they give as well. If alpha errors means that false positive errors, so the boy cries wolf and is over and over and over saying that, you know what, there is positive, it's positive, it's positive, when it actually isn't, right? So I give myself some trade off and keep alpha at a reasonable level. Okay, hope that makes sense, right? So now we understood this page. Okay, now we come to confidence intervals. Okay, so we looked at alpha and beta. We looked at the trade-offs. We understood what everything means. Okay, but there has to be a way to clinically, like actually, mathematically quantify this. Okay, so the question, that problem that arose was, how do I measure this? And that measurement is called confidence interval. How confident am I in my decision or in my study? Okay, whatever I've done, right? What is confidence interval? This is CI, which is 1 minus alpha. And what was I looking at here? 1 minus alpha, right here. Okay. So this is my confidence interval, right? So if I keep a draw a straight line right here, okay. So this will, to the right side will be alpha, and to the left side will be 1 minus alpha. And this is what I've drawn here. Okay. You see this, right? This is the null hypothesis, right? So the confidence interval, let's just read for a second. Range of values within which the true mean of the population is expected to fall with a specified probability. Okay, so you see this diagram again. So this will be, if I choose this will be where the true mean will fall in this range. Okay, and the probability will be determined and my alpha and beta levels will be set. Okay, so ci is equal to 1 minus alpha. The 95% ci that is corresponding to alpha is equal to 0.05 is often used. Okay, we want to make sure 95% of the time we are confident in what we are achieving. All right, as sample size increases, ci narrows, right? And the thing is, even though I am introducing this graph here, let me give you confidence interval graph. Okay, see something like this. Okay, so it's not actually measured within the null hypothesis and that graph. Okay, that was just like a different graph, but it's measured like this only, right? And if it's just, this is like a two-tailed, okay, you have two tails and stuff, but you see, so so when what I'm trying to do is I'm trying to gain confidence in my study. And how do I gain confidence in my study? Is within this limit, right? Within this upper limit and lower limit, I should have about 95% of my data. And that if 95% of my data falls into this range, I can assuredly tell myself, you know what, this data is valid. But if it's at the extremes, again, this concept will come back over and over. Okay, that if it's at the extremes, it's not gonna mean anything. All right, it's too extreme to even consider, right? So we look at confidence intervals now. So this is the alpha level. All right, so at alpha level 0.05, I've drawn this line, and this is the extreme value. Okay, and we don't need this. And what do? Screw the extremes. Okay, this is the we are good curve, right? 95% time we are good. So how do we actually generalize and make a formula based on this distribution? Is we take the mean, all right, the populational mean, the true mean, plus the z score multiplied by the standard error. Okay, and you'll see this here as well, right? Mean plus or minus the z score depending on which side of the mean you are, and the multiply the z score by the standard error. So what are we actually doing? You see in this graph, okay, so the z score is basically like, for a normal 95% of the data is basically 1.96 to 2.58. Yeah, so 95% of the data should fall into a z score of 1.96. If it's doing that, then we have a good and like really valid data. Okay, that's what the confidence interval is trying to say. And 99% of the data should fall into 2.58. Okay, so that's the z score. And once you have this, you add the mean and subtract the mean, you get that. So that's why you see this upper limit is 5.62, but the mean is 4.27. If I put these values in the thing, I can calculate the z score and stuff, even though the standard error is not given here. See, so you take the mean. If it was 4.27, I'll put 4.27 here. All right, if I don't know the z score, I'll or if I want to find the standard error, I'll put in 1.96 here, and the confidence interval is positive, so I put 5.62 over here. Okay, then I try to find the standard error. But if the standard deviation and sample size is given in the question, I take the standard error. Easy. Take the standard error. They want 95% of the confidence. I put in 1.96 or just put 2 in there. Okay, you'll get the good approximate result. Then they'll give you the mean. So what are they giving you? They're either giving you 3 things or they're giving you 4 things. What are the 4 things? They're giving you the mean. Okay, they might give you the z score or they might not, and they will either give you the standard error as it is, but it's kind of easy. They want you to remember this formula. They will give you standard deviation and the sample size. Okay, don't look at the question blankly. Just identify what are the things that they're giving you and try to remember at least the formulas that correlate to this thing. And they're gonna ask you like, okay, what is the confidence interval or something like that, right? Even though I haven't seen questions on confidence interval, they just ask you the intuition behind them mostly. Okay, so these are the confidence intervals. Okay, and confidence interval plots matter a lot. So I'm going to try to explain this thing right here. Okay, and a lot of questions are asked in these things. Okay, so we've seen this. Now, there's three scenarios in which confidence interval actually helps me, or it can like rule out stuff. Okay, what are these three scenarios? Okay, the three scenarios are the mean difference. All right, the difference between the means of the study that I'm conducting. Let's say I'm trying to test drug A and drug B. Okay, I draw their confidence interval graphs and I get their mean and stuff, and I try to find the difference between the interval. Okay, the confidence interval. Okay, that's the one scenario. Second scenario is when I'm measuring odds ratio. Okay, what do we do odds ratio in case control study, right? So in some case control study, or some like if I'm measuring relative risk and stuff, right? If I'm doing those studies, right, in which, let's say for example, you have exposure, okay, or I'm testing for intervention, or I'm testing for risk based on some disease or something, or some other thing, right? If I'm doing that, then there's another scenario. Okay, and then confidence interval between two groups of the same like categories. Okay, so let's say I'm measuring blood pressure range, or like mean blood pressure in female population and the male population of a certain age or something, right? Then I draw the confidence interval between those two groups. Okay, so these scenarios determine what the confidence interval can be. Okay, and how do we actually gauge if something is important based on these confidence intervals? Okay, and what is actually statistically significant? If the difference in mean, okay, you see how this was a study about like some weight loss or something, okay, and this is the frequency basically, and this is the amount of kg they actually lost or gained or something. Okay, so in one patient population they found that they gained 2 kgs. In other patient population they found they lost 4.2 kgs. Okay, now understand that between minus 4.2 and 2 there is a zero value. Okay, all right, if there is a zero value in between, what does that mean? That means at one point there was no association, right? Nothing happened, right? um, your drug or your weight loss program or whatever you offered didn't work at all. So how can I trust your study? And that's the first scenario they talk about right here, right? So um, H naught is rejected when 95% of the CI mean difference excludes zero, and that should make sense. And 95 of the CI of the mean difference excludes zero, and that why H naught is not rejected, right? So why is it not rejected? Because I don't have enough proof. What I've basically said is there is a point in my study where there is no association, nothing happens, nothing is good, nothing is bad, right? And what do I determine? Did it work or did it not work? So every mean interval, okay, every difference in mean should not contain zero. If it contains zero, then there was a point in the study where it didn't do anything and no association is defined. Okay, and it makes sense, right? If I just go through certain examples of stuff like this. Okay, you see, if something is gaining weight in one population and something is causing a loss of weight in another population, well, what are you doing? Are you helping or are you removing? You know. Similarly, if a drug is increasing the blood pressure in one group and decreasing the blood pressure in another group, and if I look at the thing, what are you actually doing? You're not doing anything, right? That is the confidence interval that we use to help us figure out if H naught is rejected or is H still proved. Okay. So difference in mean. How do I know actually anything actually significant happened? How do I have confidence when there is no point? When there is a point of no association, neither positive nor negative. Either you go all the way to the positive side, either you go all the way to the negative side. At least I'll know you're causing an effect. Zero is no cause, no effect, right? What's the next one? Odds ratio or relative risk. And I've emphasized this point as well. If odds ratio or relative risk is equal to 1, that means nothing happened, right? If RR is equal to 1, there is no association between exposure and disease. If odds ratio is equal to 1, odds of exposure are equal in cases and controls. Well, I haven't found anything. If I don't find anything, and if I try to build confidence, like if I try to plot the graph based on the mean and the standard error and stuff like that, I try to draw the graph of the sample. What am I gonna get? It doesn't make any sense. It's not gonna be clinically significant or statistically significant. Okay, and that's what the second criteria is. The three scenarios. Okay, and then you have something which can look like, and what have I written here? If after calculating the risk, exposure is odds ratio of 2.5, how do I confidently know this result? Okay, the CI must be greater than 95%. Okay, so there's two things that come in the picture when we talk about ratios and stuff. The one thing is that this either should be greater than 1 or less than 1. It cannot equal to 1. That's the one thing. Second thing, I should always check my confidence intervals. Okay, if they say if they say that the confidence interval is not 95%, okay, or my alpha value is 10 or 20 or something, that data is not valid. How can I have how can I have invalid data and try to build confidence interval on top of that? Okay, so always check twice to first confirm the alpha or the confidence interval. Okay, once you do that, check the OR or the RR or the mean difference and stuff like that. Then you come back to this. Okay, now so in all of these scenarios, what we're doing is we're trying to compare these two things. Okay, we compared the mean here, compared the mean here, compared the exposure here and the risk here, right? And yeah, so we got the two ratios here. We're always comparing. So what if in our comparison the two confidence interval graphs of the two different things overlap? Okay, that means that the all the data points, the frequency that was present in the purple graph also matches the frequency that is in the blue graph. That means what have I actually found? If they overlap, I have not found any like significant detail, right? You haven't obtained any clinically significant conclusion. Need further investigation to actually come up with some confidence interval. Okay, interval means the difference between the two. Okay, the two peaks. Well, what is the difference between these two peaks? There is no difference. Confidence is undefined. It's zero. Okay, so I need these two peaks to move apart or closer to each other or move away to left or the right. Okay, that is the confidence interval. Okay, I hope all of this, even though it's not like pure statistics and I'm not like trying to teach you like pure statistics, all of this I'm trying to make intuitive sense for you. Okay, and how to help you like actually solve these questions, because I used to get these questions wrong until I understood what or basically formed in my head what the idea actually is, right? And we can use this to solve these questions. Okay, um, Gemini gave me a good result and I'll share this with you. This was a trade-off thing. So how does increasing alpha increase power? This is what I asked, right? So increased power is I think it's a he or a she, I don't know. So they defined power first. Okay, with higher alpha value, the rejection region of the test statistic widens. This means a wider range of results will lead to rejecting the null hypothesis, right? In simpler terms, it becomes easier to find a statistically significant result, potentially increasing the chance of catching the real effect. And what is the analogy I gave you? Alpha increases, the wider the net becomes wider. Okay, the catch, increasing in type 1 error, gives you a drawback, and the balance is this thing. Okay, you can go through it. Better ways to increase power, increase the sample size. Alright, so now I'm sure a lot of people get confused on these things. Okay, because I used to as well, right? This common statistical test, and this will be our last thing. And before I go into this, what we have to talk about are variables. Variables are unknowns or things under observation. Okay, variables. So classify your things. So if you have a group of toys, you're gonna classify your toys as well. All the race cars go there, all the dolls go in that place, and this and that, right? So how do we classify these variables? So variables can be either categorical. I can put them into categories. These are the group of blue toys. These are the group of yellow toys. These are the stationery. This is that. This is that. Different classification based on different categories. Categorical makes sense, right? And what is the question they this categorical ask is, can they be grouped? If they can be grouped, like I can be grouped in a bunch of humans, right? Humans, elephants, dogs, cats, they can be groomed, right? So if they're grouped, they fall under categorical. Okay, and what cannot be grouped? Okay, and what is the next division of these variables is called quantitative. Quantitative is measuring the quantity of things. They cannot be grouped. And usually quantitative, what it asks is, does it have like a numerical value? Okay, your weight, your height, your BMI, your like the distance between the school and your house, anything like these things can be quantified by some value, right? Some numerical value. So that is quantitative. So they all of these values, like all of these study values, fall into these two categories. Okay, how do we sub-classify this categorical? We divide it into nominal and we have ordinal. What does nominal say? Do you have any order or a hierarchy? Sorry. They ask you the question, but it says do not have any order or hierarchy. Okay. So nominal don't have any intrinsic order. Okay, and what is that? What are the examples? Like blood types, car brands, right? I have Toyota, I have Hyundai, I have Mazda, I have Volkswagen, I have this, I have that. Can I create a chain saying, you know what, Toyota is greater than Hyundai is greater than this, and once I reach Toyota I have to get Volkswagen, then I get this, then I get that? No, there's no actual relation in between. Similar with blood type, I have either alpha, I have beta, I have O, or this and that. I cannot make a hierarchy of, you know what, alpha is the greatest, then beta is in second place, and then O is in third place, and then this and that, right? So nominal, it doesn't have any order, it doesn't have any hierarchy. But you look at what ordinal is, O for order, okay? Ordinal. It has some internal hierarchy, 5-star ratings, right? All your ratings, all your educational levels. I was undergraduate, I became a graduate, postgraduate, PhD, whatever. So there was a internal hierarchy, and I suggest just go through and type in like examples of nominal data, ordinal data, categorical data. This will help you remember stuff. Okay, why am I going through this? I'll let you know right now. Quantitative, are there the number of things? Now, are there discrete packets of things? Okay, number of siblings, number of cars, number of pencils, number of staples, whatever, right? All of these are discrete stuff. What is the other category? We have continuous. They have series. They have series of variables. Okay, so what is this? This is like height, weight, temperature. um, Weight is categorized into kgs, right? Height is characterized into inches, feet, or meters, centimeters, whatever, right? Temperature is Celsius, Fahrenheit, Kelvin. So most of the measured data falls into this. Okay, and you will see that you have like this also can be like 2.3344455. It just keeps on going for infinity if it needs to. So all of those data also falls in this subcategory. Okay, so now we understood categorical and quantitative is. Other one that I tried explaining before as well is the independent and dependent one. Let me Yeah. So independent was explanatory variable, dependent was the outcome variable. I change this, this is the cause, right? I get this is the effect. Okay? Independent variable, dependent variable. And what are the things that can modulate the effect of these two? It's we have control variables. Control variables only affect the dependent. So this is they affect the effect. Okay, control variables are important when it comes to dependent. Confounding variables, as I said before, they affect the both cause and the effect. Okay, and moderator variables for false strength of association and slash moderation. Okay, so they usually affect the independent variable. Okay, all of this to better understand how we actually divide and visualize data. Okay, so if I have categorical data, that means I have categories, right? What kind of categories? It could be dogs, cats, it could be males, females, all the genders. It could be phones, laptops, or something like that. All my study is conducted based on that, right? So all of those data. So if I have less than two, you see this, now we're here. Okay, If I have a small sample size or less than two categories, basically, I use the Fisher exact test. Okay, small sample size or less than two like categories, or like yeah, greater than two, or I think is the main cutoff or something, right? So Fisher exact test is basically saying, you know what, I'm going to find the relationship between these two categories and stuff. Okay, so you make a 2 by 2 table, or and some examples are like yes and no questions. So I make like a survey or something. So what do I use in terms of, like, if I do need to use that, I can use the Fisher exact test to like conduct my statistical analysis, right? If I have more than two groups or larger sample size, okay, what do I use? I use the chi-square test. And again, you see the example I've given here is the eye color. So eye color is, you have different shades of eye colors. First of all, more than two groups, and you can have a large sample size when it comes to that. Okay, don't get confused in, as I said, survey, but the thing is, you're just asking one question. Okay, do you have this? Yes or no? Are you suffering from this disease? Yes or no? And then you use the Fisher exact test on that question alone, not the whole entire survey. Okay, chi-square test. Okay, if I want to show you guys what it actually looks like. Right, so the table looks more or less like this. It's just like exposure and outcomes and stuff like that. Okay, and then they do analysis based on this. Nothing too fancy, but the fancy one is the chi-square. See this? So this is basically giving degree of freedom in this case, but see the yeah, this is the formula, and this is also giving us like the association between different variables, different categories and stuff. Okay, so those were the categorical stuff, right? Now what is left? We have the numeric data. What do we use in numeric data? If I have two groups, okay, two groups of data, I use the t-test. Now in the options, they might give you t-test based on pairing and unpairing. Okay, what is a paired t-test? A paired t-test is basically the example I've given here is BP before and after drug, right? You see how the event is giving the drug, but I'm measuring the two numbers that I'm measuring is BP before and BP after, but those two are connected, right? So that is a paired test. Okay, paired t-test. What is an unpaired t-test? BP in men versus BP in women, different, separate values. Okay, they're not together. Okay, so that is the t-test. We always use it when you have two groups present. Okay, what is the ANOVA, analysis of variance and something so difference in means of continuous variables. So glucose in type 1 diabetes, in type 2 diabetes, and in healthy patients, what will I use? I use ANOVA. Okay, I'm going to measure the glucose levels, right? It's first of all, I'm getting a number, numeric value, so I'm going into quantitative analysis, right? And in the quantitative analysis, I have greater than two groups, right? And what am I actually measuring? I'm measuring the means of all these variables, right? And what are these variables? They are quantitative and continuous, right? So I'm measuring in ANOVA. I'm using these variables. Okay, so ANOVA, let's see it here, greater than 3 or plus groups. And the one thing that they might try to they have added here, right, correlation stuff, is this, right? So correlation tests, you have two correlation tests. If it's a normally distributed data, which most of the time for us is going to be the normally distributed, we use the Pearson's correlation. Correlation is basically finding association or linkage between two continuous variables. Okay, two quantitative variables. Okay, two quantitative variables. So both of them are numbers, and I'm trying to find the link between these numbers. Okay, if it was a categorical and quantitative, Okay, so if it was something like this, right? So if I take a categorical variable and I take a numeric variable, for example, if I was measuring house prices in terms of number of bedrooms, okay, that's a common regression problem. Okay, so these two will come together, and how will I analyze them? I'll use a linear regression or logistic regression or something like that. I use regression. Okay, correlation is basically two types of quantitative data that I'm seeing. Okay, so correlation between sleep, the hours of sleep, and the academic performance, so basically a grade level, and I'm trying to find a correlation between them. Okay, and what do I actually do? This should be simple now. If it's positive and facing going upward, it's a strong correlation. If it's negative and it's going downward, it's a negative correlation. No correlation and it's scattered out about randomly. Negative correlation, guys, find, you can see the difference between these two, right? You see how they're not packed together, right? Compared to this, right? They're not packed together, and although the slope is negative, so this will confirm to me that this is a weak negative correlation, and here I have a positive, weak positive correlation. Okay, there's not too much to like harp on about this thing. It's pretty easy. Okay, positive R values, positive correlation as one variable increases, the other increases, and this is giving us some simple stuff. And again, I have positive and negative values. So if I want to find this coefficient of determination, I'll square the value amount of variance in one variable that can be explained by variance of other variable. So once I square the values, I'm going to see how changing one variable can change the other variable. Try to find the proportionality between the two. Okay, and that's it. I hope I've covered most of the content. Meta analysis isn't that hard. It's just having studies over and over and over by different people, and you can go through this. What I always recommend is, if you're reading through this, right, stop the video and go to your favorite GPT or something and type in these things and ask it to give you examples. The more examples you look at, and these are not enough, okay? Obviously, these are not enough. The more examples you're going to look at, the easier it's going to get for you, all right? And obviously, keep solving questions. And all right, wait, I haven't discussed this, and I think I made a note of it as well. Kaplan-Meier curve, yeah. So Kaplan-Meier curve is basically the graphical representation of event probability. So this I'm choosing between like a exposure or like a treatment and a control group. Okay, and what I'm looking at is the probability of something happening. When I give the drug, the survival was at this level, but to those I didn't give the drug, it decreased at this level. Okay, and they can give you this curve in like a number of experimental type questions, and you just have to figure it out, because what's so hard in trying to figure this out, right? You see, when I give the drug, the patient is around 9 or 8.5, like 0.85 percent like survival probability. But if I don't give the drug, they're just at 50% or something, right? It's not that difficult. So what are we measuring? So event probability here, event probability, some adverse event or even a good event, okay? And the time, okay, length of time, useful for displaying time to event. Okay, we understand. Outcomes examined may include any event, but frequently include mortality. Survival probability is equal to 1 minus event probability. In this case, it's an adverse event, and we're looking at survival and stuff. It could be something else as well, but make sense of it. One is the entire probability, okay? The the probability of that event occurring minus the entire thing will give you the survival thing, okay? Event has to be an adverse event, okay? Only then will you get the survival. We've gone through the likelihood ratios and stuff. Yeah, pre-test, post-test probability and stuff, they might not ask you to calculate and stuff like that, but they might ask you the concept behind it. Okay, likelihood ratios are just there to guide your pre-test probability, right? And it helps you to basically differentiate between the exposed group and the unexposed group. Okay, So patient with the disorder or patient without disorder. And I think we've covered most of this. Bradford Hill criteria, off-label drug use. Yeah. All right. So we're good.